All right, good morning and happy Wednesday. It's September 13th, and I'm planning on doing the LeetCode Daily Challenge for today. So I'll share my screen here and we'll start jamming. Okay, so Candy. Let me solve this one. It was like, let's do this. You set to default before I look at it. Okay, and it is 4:47 a.m. Okay, ratings. This child has one candy. They get more candies than their neighbors if they have a higher rating. This guy's higher than that guy. This guy's higher than that guy. Return the minimum number of candies. 8. 1. This guy gets 1 because it satisfies the two conditions. Strictly higher. So here it's not higher, so you have less. Hmm. Each of them have to have at least 1. There's 20,000 of these things. 70,000. Okay, so what is the game plan then? Right? How are we going to solve this thing? So it seems to make sense to go from the bottom up, right? So we assign the first candy to this dude, right? And then since this guy is strictly greater than, it has to have +1. Right? Since children with higher ratings than their neighbors. And this is a corner case where this only has one neighbor and it's not greater than it. Okay, so let's do this. Let's do BFS. How about BFS starting from children? Oops. We give one candy to, so that occurs, initial kids would be, let's call this guy an array A. Each ith value of the input array A, right? Each ith value of the input array A, such that, oops, such that a sub I minus 1 is greater than or equal to a sub I, and a sub I is less than or equal to a sub I plus 1. So its adjacent neighbors are either equal or bigger, or they don't exist, right? Or I minus 1, I plus 1 is out of bounds, right? So out of bounds would be this case. Okay, and then from the initial kids, right? From initial kids, expand outwards and update adjacent ith. value to be +1 from previous. I think, I don't know, it seems feasible, right? Let's see what happens. This one's a hard, so I mean, maybe I'm missing something, but let's see what happens. That seems like a decent game plan. Okay, so it's 4:52 a.m. So that took about 5 minutes. Game plan, let's do the implementation. And as the cardinality of array A, and then we'll have each ith rating that will initially update the Q to B. So let's do this Q. Q and then scene, I suppose. Q can be our deck. Scene will be a set for each ith value in the A's range, 0 to n-1 inclusive. If 0 a sub I minus 1 is greater than or equal to a sub I, and I plus 1 exceeds n, meets n, or a sub I plus 1, a sub I is less than or equal to a sub I plus 1. This and that, then it's part of the Q. And the ith value. Scene add ith value, and then T candies we need will be minimized as we crudely consume them from the bottom up. We'll T at the end here, and then Q, right? We'll do the BFS outwards, minimum onwards. So adjacent neighbors are just selected to the right of the linear picture. So ith index equals Q dot pop left. So for Jn plus or I minus 1 plus 1, right? Since these are adjacent neighbors, if J is in bounds and J is not seen, then consider a sub I compared to a sub J. Well, actually, so near the Q is these guys. Is it a safe assumption to say, hey, these guys are strictly greater than? I don't think so. So we need to have a check, right? Could come into a plateau where they're all the same, in which case we could have ones assigned to them. Oh, wait, hold on. Now, if they're all the same, they'd still be captured here. Like that plateau would be captured here, right? We see the jth one more than once there. Hold on, I'm thinking we need to reconsider J. Right, so I'm trying to think of the use case, imagine in my mind, like what can occur. I'm thinking, what if we assign a value to J, but then we need to increment J later on? And so what if we have 3 is to say 1, 3, 4, 5. Okay, so that needs to be 5, but then In the other perspective, maybe we only have like a 5. So these are our indices. So this ith index will be added to the queue, as well as this ith index. So when we update adjacent j's, this guy initially be updated, right? So initially, the smallest guys will be assigned 1s, right? Oops. And then we'd assign this guy at 2, assign this guy at 2 as well, assign this guy at 3, assign this guy at 4, and then this guy would need to be 5. It need to be updated to 5, right? So there's 2 updates here. Here. It'll be a void updating that thing twice. But we can only add it to the queue. Let's see. We only want to go up. Right, we only want to go up when we go through the queue. Okay, so scene is fine as long as we go up. J is not in scene, and a sub I is strictly less than a sub j. Right, we want to go from the bottom up. Right, and that would prevent this guy from being updated twice. It would only be updated once. I think that works, and we'll see what happens. Maybe I'll submit it on some sample inputs. Okay, so ith value. Okay, so J will be appended to the queue and marked as seen when this occurs. And then totals we need to update. Okay, so each value in the queue and the cost associated with it, then cost 0 using cost using cost sub I equals 1. Cost sub j equals cost sub I plus 1. Okay, so we don't need t, right? We'll just turn the cumulative sum costs. Okay, so let's walk through the sample input and see if this works. I think so, right? Implementation is done pretty much, right? So, it's not 5 o'clock right now. 5 o'clock, 8 minutes. Implementation, plus consideration cases. Right, so this guy can put the algorithm basically. I have number 1 right now. Step through input. Code, step through code, examples. Trying to figure out where all my time is going. So eventually I can be hopefully a contestant in the LeetCode contest. So the cardinality for input array A and is 3 for example 1. So for each ith value, I'm going to say, hey, okay, this guy, is it less than or equal to its adjacent neighbors? No. Okay. Is this guy less than this adjacent neighbors? Yes. Q is initialized with 0, which has been seen. The cost of 0 is 1, or cost, it's actually index I. It's 1. This guy is not strictly less than or equal to its adjacent neighbors. Okay, so Q is 1 and cost is 1. So adjacent neighbor J is I minus 1. A sub I is strictly greater than A sub J. It is. So the cost of 0 will equal 2, and the Q will be dq1 in Q2. And also in Q, or I think we do 0 in Q2. Cost of 0, cost of 2 is also 2, right there, plus 1. In the previous height. Okay, so that one works out. And then the other one, example 2 is 1, 2, 2. Oops. 1, 2, 3. Okay, so this guy is strictly less than, as well as this guy is strictly less than, right? Less than, or greater, yeah, less than or equal to its adjacent neighbor. Okay, so the Q is initialized with index 0 and index 2. So cost of 0 is 1, cost of 2 is 1, and then the cost of 1 would be 2. Okay, I think that works out. Let's see what happens here. Okay, that looks good for Q1, Q2, and then let's come up with maybe some bigger input. One that goes up, stays the same, goes back down, something like that, and then maybe one with the middle. Something like that. Let's see what happens. Okay, that looks good. Submitting 504. Uh-oh. 504. Zero. So plus 5. Oops. What was when I officially submitted? It took like 17 minutes. Zero. Let's see what's going on here. Sample input worked, and a couple of the other things worked, but this one, let's see. So this one goes up and down. Output's 9, but expect 11. So what's going on here? Why is this failing? Here's our input array, right, for the failure test case. X5. Q will start off with 1, or get the 0 index, and this guy. So cost of 0 is 1. Cost of 4 is 1. And then jth indices adjacent to these guys. So let's say these guys are plus 1 each. It's 2, cost of 3 is 2. Then we'll see this guy. Wait. Hold on. Oh crap. Okay, so yeah, this needs to be updated more than once then, right? Can't check that guy. Okay, so remove scene, right? And then just update adjacent values multiple times, right? Maybe 2x at most. That should be okay as long as we're going up. I think so. I think that's okay, right? As long as we go up, right? So it has to be bigger. All right, let's get rid of scene. And so based on that failure, it seems like just update these values multiple times and remove the scene constraint. Okay, this guy. This. Make sure we don't have any regressions. We'll keep those in our back pocket. For now, just validate this single test case without seeing. Uh-oh. Let's see. We don't want scene. Right, so we have a Q and we have their cost. Q is populated with the lowest values. Cost is updated more than once. Okay, that looks good. It turned green for that test case. Let's see. Make sure we don't break anything along the way here. Make the sample examples should still work. Okay, this looks good. Let's see what happens. It's 508. Okay, that's accepted. Yay. 508 accepted. So total electric from 447 to 508. 508. It's like 21 minutes. It's total. Oops. And then plus one bug. Oops. Oh well, it happens, right? I'm not perfect. I'm work in progress, so it's cool. Okay, so let's see. Previously solved this about a year ago. It looks like I haven't solved this. Wait, no, I did do it in Rust. Okay, so ooh, I even did it in Java. Well, let's see what I came up with previously. Like this seems like a decent solution. Have a queue and then do BFS to adjacent neighbors, which are strictly increasing. Okay, let's do this. Oh, I did dynamic programming, really? Wait a sec. It's pretty similar. How is this dynamic programming there? Hmm. Value is strictly greater than. Oh, we go left to right and right to left. Interesting. Greater than constraint. Hmm. So I goes from left to right, J goes from right to left. And if the previous one to the left is strictly less than, and the cost is of that previous one is greater than 1 plus the adjacent neighbor. Interesting. Okay, so yeah, this one's more efficient than and more simple than what I came up with today. From the past, I'll be like forward, way like the future. It's monotonically increasing, say, incremental cost. Oh, okay, so this guy does 2 linear scans and Maybe we just need one, right? Yeah, okay. It takes some time sometimes to refactor the code and come up with a more concise solution. Line these things up. It seems like the code would be easier to read if instead of ordering it by index, do it like this, try to express the inequality this way so the code lines up, make it easier to read. This guy is less than that guy. Yeah. Sometimes, yeah, just small changes like that can make a big difference, I think, in the readability. You can see how it aligns up this way. That was cool. Right. Previous solution. Solution from a year ago. Seems to work out right. That's cool. And yeah, this is a cooler solution, right? One pass, this is two pass. So maybe I should have spent a little bit more time to try to optimize this before I looked at my previous solution. And sometimes if you look at a previous solution, that's like all you can see, like the cognitive bias is geared towards that one and only way of solving this problem. Here's GP, right? Or the past from like the future. This one's kind of the similar way, but it's more like a greedy approach. Okay, let's start bottom up and go up, right? Bottom up seems to intuitively make sense in that each child needs at least one candy, and then adjacent neighbors with higher ratings get more candies. So yeah, start bottom up and then go that way. Okay, well, yeah, I did this in Rust. So that's cool. I don't know if I want to align these things or not. I think I do. And this is pretty ugly code. So yeah, let's just line these things up here real quick. Update the solution for enhanced readability. And I mean, this code is just ugly. Right, look at this. I mean, yeah, the ith index is over here to the right. This I minus one index is to the left, and similar to this thing, but I think it's more beneficial to align the code this way. Right, this is easier for me to read. So I goes from left to right, J goes from right to left, and it's basically the inverted consideration, right? Okay, so let's do that. Let's do this. We'll just copy and paste these guys and then update them real quick. And then go study something else, probably linear algebra for machine learning. Okay, so here's the solution, and we'll just get this guy to line up with that guy. That up. And line this up. So that's aligned. Alva. Alva is Kotlin's verbose cousin, I think. Okay. This guy here. Okay. This guy here. So it's all lined up. Oops. I think that's easier to always see the less thans too, right? So when we think of monotonically increasing values, or we think of writing values, we go from left to right intuitively here. I mean, that's how we read and write and think of things, right? So in the code, it also, I think, is less cognitive demand, right? Less cognitive load if we have consistently, okay, this thing on the left is less than this thing on the right, right? The code lines up too. And of course, that's my own subjective opinion, and other folks might have different opinions too. We're each entitled to our own, right? So there's a lot of times there's no right answer, just different perspectives on the same thing, which is okay, right? And this guy, J, and this guy is less than or equal to X. Less than or equal to that guy. Okie dokie. JavaScript. The update Rust and C++, and then we'll call it a day. Rust. So G+1 is strictly less than A sub J. And then the cost of I minus 1 is strictly less than cost of I. Oops. Oops, I minus 1. Right, so that's just the adjacent neighbor to the left, and then the adjacent neighbor to the right. I mean, linear scan from left to right, right to left, correspondingly. Okay, so this one is okay. Okay, and then we'll do C++, and then that's all she wrote after this. Okay, so these are the jth values. Strictly less than that guy, and then it's less than or equal to so minus 1. Okay. It's good. Oop, all right. Update. Okay, accumulate the sum at the end here. All right, that's all she wrote. Catch y'all later.